Swanns method work with something like this, right? You first of all begin with an arbitrary point. The first point that you sample on the function, right? You have to essentially start with 3 points, right? The first point you have to select. So this point is arbitrarily, or randomly, first point is randomly selected, right? So whatever the interval is, you randomly select the first point, and once you select the first point, then you can start. What is typically done is, okay, you will add, so this is the first point, right? Let's say this is x0, you will add delta value, which is a parameter, and then you will find this point and you will subtract delta value, okay, and you will find this point, right? So that's how you will, once you have randomly sampled, that's how you will add the delta and subtract the delta, and you will get the 3 points that the algorithm should start with. And once you get these 3 points, you sample the function and you look for the 3 cases that they belong to, and then you decide whether to move left, right, or to stop iteration, okay? So again, things to remember, x0, which is the beginning point, is arbitrarily selected. Delta is a step size parameter, and this is something that you have to provide to the algorithm. And q is the counter. Counter in the iterative counter, iteration number is 0, this counter will be 0, iteration number 1, this counter will be 1, iteration number 2, and so on. And again, we will go through all of these counters and all the other aspect of this algorithm using a specific example problem, which will make it even more clearer. This is the way we start. What we do, we start with initial point and a step size delta which is defined, and this is something that we begin with, okay. Then what we do is we find out the x plus delta, x minus delta, those are the 3 points. We evaluate the functions at x0, x0 plus delta, x0 minus delta, and then we evaluate all the 3 different cases. So you can implement this as a case or as a switch in your overall algorithm, so where you're looking for 3 different cases, and using this you will check whether this condition, the first condition where the x0 minus delta is greater than fx0, which is greater than fx0. If that's the case, we need to move to the positive or the rightward, right? So the right is positive where the delta is positive, so we are going to increase and keep moving towards positive direction, which is this direction, or the right direction on the axis on the plot that we have been showing. If we fall into the second case, which is function values are essentially decreasing as we are moving from left to right, right? So in that case, what we will do, delta has to be negative, so we have to move in this direction. Rather than moving in this direction, we are going to keep move in this direction. So that's the second case, if that's the possible. And if not, if you fall into the third case, then we know that we have bounded, and the bounding search terminates, and we basically output the x1 and x3 values, which is like the lower and upper interval, and that gives me the bounding interval that I should be focusing on, okay. So let's take an example problem, test problem, to understand all the steps that we have listed in this slide. So let's begin with this function, right? So this is a function that we want to basically bound, and so what we want to do is we want to find out an interval within which the optima to this, and we are trying to minimize this function. So when we are doing bounding, at least it is assumed for this one we are minimizing it, okay. So we randomly, let's say, selected an initial point x0 which was equal to 1, and let's say the magnitude of delta, we set that at 0.5, and these are the 2 things that you have to begin the algorithm. So this can be generated using a random number generator, and this could be something that you have to specify as a user, what is the step size or the delta itself. So let's say we have specified that to the algorithm to be 0.5, and let's say randomly we started with an initial solution at 1, then how does the different steps of this algorithm, which is the Swanns method, will help us in bounding the function fx equal to 2x squared plus 16 divided by x itself. So let's get started. So we know that x0 is 1. So first thing that we can do is we can sample the function fx0, right? So what we will do at x0 equal to 1, we will substitute 1 here, which will be 2 1 square plus 16 divided by 1. That's what is written here, 2 1 square plus 16 by 1. So the sampled value of the function at x0 came out to be 18. Now recall, we have to add positive delta. So if I add a delta which is 0.5 to x0, then x0 plus delta becomes 1.5, right? Now I will take this 1.5 and substitute that in this function. So that will be 2 times 1.5 square plus 16 divided by 1.5. So if you simplify and do the calculation, that should come out to be 15.17. Similarly, we have to also do the third point, which is x0 minus delta. Okay, so if I subtract 0.5 from 1, that is going to result in 0.5, and if I substitute that here, which is 2 times 0.5 square plus 16 divided by 0.5, I will get 32.5. Okay, so now I got the function samples at x0, x0 plus delta, x0 minus delta. And in the example that we are showing, right, essentially what these are, this one is fx1, right, this one is fx2, and this one is fx3, right? Those are the 3 points where x2 is equal to x0, x3 is equal to x0 plus delta, x1 is equal to x0 minus delta, right? So those are the 3 points. Now, using these 3 sample values, we can compare those function values and find out which case we belong to. So looking at this function samples, we can see that this is fx0, right? And in the plot that we are trying to do, right, remember the plot where we want to determine the different cases, looking at this function sample values, you can see that x0 is here, right? So fx0 is here, and this value is going to be 18. fx0 plus delta, which is right here, is 15.17, right? So this is 18, this value is 15.17, and then fx0 minus delta is essentially equal to 32.5. So we can see in the pattern is decreasing. So according to our case scenarios, we know that the function values are decreasing as we are moving along in this direction. So we should be moving in positive direction or in the rightward direction, right? So that's what we are going to do, is we will see, we will fall into this condition. Therefore, the delta must be positive, right? So delta has to be positive, and we move in the right hand or the positive direction that is out there. Okay, so that will be the step that we will do. So once we implement that step, then we will use the Swanns iterative formula, which was listed before, to find out the next point where we should be doing the sampling. So let's go ahead and do that. So this is the function, right? What we are going to do is, if you recall, the formula that was given to you for the bounding algorithm was that xq plus 1 is equal to xq plus 2q delta, right? So now we have come into essentially the iteration 1, right? First initial was the 0th iteration. So when we come into iteration 1, right, the x2, so the q value will be 1, the index of the q will be 1, so the x2 will be given as x1 plus 2 to the power 1 delta, or x2 is equal to x1 plus 2 delta. So what we are going to do is we are going to find the next point using this equation, which is listed here. Okay, we had x0 equal to 1, we had x0 plus delta equal to 1.5, but the third point in the iteration number 1, right? Now we are moving into iteration 1, whereas the previous case, right, the iteration was 0. So in the previous case, the iteration index was essentially q equal to 0, right? So now here we found this, and then we have already computed fx0 plus delta in the previous one. The only thing that we need to do is compute this new value x0 plus 2 delta, which is equal to 18.9. Okay, and look into the case. Now if you look into the case, what is happening, right? We are falling into the case where probably this fx0 is right here. Fx0 is right here, fx0 plus delta is right here, and fx0 plus 2 delta is right here, and I can write those values. So this is 18, this is 15.1.7517, and this is 18.9. Okay, so we fall into case 3, and we know that, okay, then this could be a good bound and we can stop the algorithm here with this specifying that these are the two solutions for the lower bound and the upper bound. And that's what we are going to do in this iteration 1. So that's what will be done typically, where in this iteration 1 itself you have been able to bound the algorithm, find the interval where the optima lies for the function that we are interested in minimizing. And that's what we are going to do. So I will just quickly show you what that looks like, in the fair way. So what we are going to do is we are going to fall into this case where we have the x1 is in between x0 and x2, therefore the optimum is bracketed, and in that case we'll basically write down the bracketing phase, right? So what is going to be the bracketing solution? The bracketing solution that will be there is that the optima has to lie between 1 and 2.5, okay? And once we find this, right, we know that the optima lies somewhere between these two values. Now we can use another algorithm to find the actual location of the optimal solution. And why this bounding is useful? Because now instead of searching from minus infinity to infinity, right, we have a simpler, or smaller interval that we can focus on, and that's the beauty of the bounding algorithm that is there. That's one thing. And the second thing that I want you to note is that the iterative aspect of this algorithm, which is we are going to be using a lot in any optimization framework, right? We started with an iteration q equal to 0, which was shown in the previous set of slides. So right here for this set, we essentially had iteration index q was equal to 0. And then we calculated and we did all the steps that are here. Now, when we found out this case, we basically, what we did, based upon the learning of the iteration that we had, we changed the location of the sample points and we basically added a new sample points, right? So this is the case where your q, or the iteration of the q, is first iteration, right? Q index is first, and then we do this calculation and we sample all the function values, we find what the case is, and based upon that we can make a decision that the overall algorithm is bounding. So we move from iteration q equal to 0 to q equal to 1, and that's the second thing that I want you to notice, that typically the algorithmic form of optimization problems will have these iterations inbuilt, and you need to get used to the iterative scheme of things that they work on.